back on. If we come back to our verification, what you notice is that it's moved from 892 to 774 now. So let's try to figure out the digital read. So we've got a bitwise shifting, and bitwise shifting, we've got bitwise and bitwise left shift, right shift, exclusive, or say the so you've got these ones that you can make use of, but why do we need them? Let's find out how. So basically we want to understand some concepts before we come to the digital read. How do we introduce multiplication in binary? If we've got a 1 in binary, on its position the value is what? 1, which is 2 to the power 0. If we shift the 1 by 1 bit, the value becomes 2, which is 2 to the power 1. So basically this one we simply shifted 1 to bit 0. You have the bit at the top. Then we shift 1 to bit 2. Bit 1, sorry. You have the bit position there. So if we shift it 2 bits away, so 1 to bit 2, the value becomes 4, which is 2 to the power 2. Same way, then it becomes 8 when we shift it 3 times, or by 3 bits. Remember, the bit starts from 0, right? So that 8, so you see multiples of 2 or powers of 2, then we've got 2 to the power 3. So actually the equivalent of the number of bits that you shifted is just basically 2 to the power. Here we are introducing multiplication. So by shifting, we actually multiply. The same way if we were to move from 8, so here is 8, if we shift it to the right, we get rid of 1, it becomes 4. If we shift to the right again, we get rid of 1, it becomes 2. If we shift to the right, it becomes 1. That is division. Going into pin 2, and this push button switch, this pin 2 is actually PD2 or port D2, right? And then we've got PD0 all the way to PD7, but we are only interested in PD2. We have no idea what state PD2 is going to be. All we know is that it's an input. It can be a 0 or it can be a 1. We are not sure. But we can make use of a reference. So our reference, we can call the reference 1, right? So a reference of a value 1. And how do we find out that particular reference? So let's say if that reference is also a binary number of, let's say, 8 bits, right? The reference ranging from 7 down to 0, we can pick the bit 2 of that. So 0, 0, we have that bit 2, the remaining being 0, may not be it. So all the way to 7. So the remaining 0. So we make sure that at least we create a reference with this particular bit set to 1. How do we do that? Just as we did earlier, we said we want bit 2, so we shift 1 2 times to the left in there, and everything else will be 0. Okay, all good. We know how to create the reference now. Now, this is the challenge now is to use this to tell the state of the switch, because the switch can be either a 0 or a 1. So what we say is we find a way. So this is our switch, and then this is our reference. So the reference, we keep it a 1. Now the switch can be 0 or the switch can be a 1. Our reference will be a 1 and our reference will be a 1. So when the switch is 0 and our reference is a 1, we expect the state to be a 0, because that is the value of the switch. So basically we want to pass this to a variable. SW was a 1, the output should be a 1. Now we notice that the only way that we can get this output, not the only way, but the one way of getting the output, this particular output from this particular input, is an AND gate. So we have the reference, and then we have the switch, and then we say 1 0, nope, both of them are not 1, so the output is a 0. 1, 1, both of them are 1, so the output is a 1. So if we check all the states, if you check all the state of the switch, you have 0, 1, 0, 1, and then you have 0, 0, 1, 1 for the reference, and the output is a 0, is a 0, is a 0, when unless maybe the reference or the actual input is a 1. So this mimics an AND gate. The top one, we don't care much about it because we are forcing that signal we are interested in into a 1 anyway. So here we have our reference. We force the reference by pushing a 1 into the bit position that we want, and then we compare the reference to the switch. So if we compare this reference using an AND gate to the switch, when the switch state is 0, our variable will be equal to 0 because of the AND. When the switch is a 1, our variable will be equal to a 1. So if we switch back, now we are on the digital read. So what I'm going to do is comment this out, copy and paste. First of all, we want to create our reference signal by pushing a 1 into bit position 2, but luckily we've named bit position 2 by a variable, so it becomes easy to identify. So we use the button pin to push the 1 there. And that we can make it simple by simply saying this. We've created a reference to the particular pin that we are interested in, and then we remember we need to do an AND to read from that particular pin that the switch is connected to. Now, to read the state of a variable, we need to use pin. So which pin are we reading from? We're reading from pin D. Which particular pin on pin D are we doing the AND with actually the one that is at position of the button pin, which is D2. So at the moment we are doing an AND with D2. So everything else will be a 0. So what have we done so far? We will look at something. Let's put this together. So far we picked pin D, which is a binary signal. Position 2, we do an AND with a 1. So let's say even if it's a 0, it's going to be a 0. If it's a 1, it's going to be a 1. So basically the resulting state, if it is a 1 of the switch variable that we had, so we have switch, is actually equal to 1, 0, 0 if it is a 1. If it is a 0, switch is equal to 0, 0, 0, which means in this case the value is 0 in terms of integer 0 value, being the 1s, and then the second one being the 2s, and the third one being the 4s, and the fourth one being the 8s, and so on. Bit 0 is 1, bit 1 is 0, and then bit 3 is a 1, which means you do multiply, that is 4 plus 0, 0, and then the decimal equivalent is 4. Which is great, but not ideal. So basically we have the switch value being equal to 4 at this point. So even though we read from it, the value is 4, which is 1, 0, 0. But all we are interested in, we want to check if the switch is a 1 or a 0. We don't want to deal with large numbers or anything. So what we can do at this stage where we have switch being equal to 1, 0, 0, of course, some byte up to bit 8, we can actually shift it backwards. So we shift it 1, 2, and then obviously back to the point. So it's 0, 1, 2. So if we shift it back to the button pin, we will end up with switch being equal to a 1 because it's moved to the right a few times. Or if the switch is off, you get switch being equal to 0. So that's one way of dealing with things. So basically, we jump back to our screen. So back to Tinkercad now, and then we say, okay, we have done this, and if it is a 1, what we have ended up with is 4, and we want to change it back to 0. So to do that, we shift it by 2, but 2 is already the button pin. So why don't we just make use of the variable? Is that the right place? Running simulation, then it works the way that we really want it to. So that's still fine. Okay, so now we want to do some digital write, right? So digital write, let's write. Whatever value that we have here, afterwards we want to toggle it. So two things we are considering. How do we do digital write? Now we know how to do a write to a pin, to read from a pin. We do an AND, because if it's a one, we get one. Now we want to do a digital write and then a toggle as well. If we have our LED and the LED is connected to bit 5, PD5. What we want is a means of a way to use our reference, which again can be a 1 or will be a 1 to the right bit position. So we will shift it into pin 5, or in this case, the LED pin, right? So we shift it to the right pin, or make sure the right pin is asserted. What we want to do is to find a way to force this to be the value that we want to set it to, right? So find a way to force it to be the value we want to set it to. So back to the truth table. So we have our LED, right? So we've got our LED pin, and the LED pin, if it is a 0, we want to say find a means to set it to high. If it is a 0, it will be a high. So we compared with our reference pin, and again our reference pin is still 1. If it is a 1, we expect it to be a 1. What kind of gates do we need to create this? So if we think about it, when this is a 0, as long as the reference is 1, so this is reference, let's put as long as the reference is 1, the output should be 1. So this is an OR gate. And then you have your LED coming in, and then the output being set. So our output can be a variable, or in this case, the output goes straight to to our LED. So to simplify things, let's look at the truth table just to remember stuff. So we have LED and then reference. LED can change from well, the pin can be a 0, or it can be a 1, or it can be a 0, it can be a 1. And then the reference, of course, will be interested in the ones only, or 0011. In this case, wherever each of them is a 1, you want it to stay on. If each of them is a 1, you want it to stay on. If both are 1 already, keep it that way. So the only case you want it off is this, and that is your OR gate. The switch, if the switch is low, we comment this out, and we say we understand a bit about the OR, but what are we doing? We're writing to the port. So we say port D, we are writing to port D, and first of all, what we want to do is to find our reference, which is to shift the 1 to the LED pin position. And then after we shift the 1 to the LED pin position, we say we perform an OR, because we are setting or forcing the value of that port. It's like writing x equals x plus 1, forcing that value of the port using the OR. So let's press on, off, on, off. That works fine for us. So far we have made some progress. Now we want to create a toggle. So if, let's say, we have a bit, which is bit 5 in this case, right? Bit 5. Not worrying about anything else. If we say we have bit 5, which can be a 0 or 1. So we have a case where bit 5 can be a 0 or 1. Equivalent. Can be either or, right? Okay, so let's say if we have bit 5 being a 0 or 1, what if we say we have our reference? So this is our reference, which is a 1. If bit 5 is a 1, we want the output to be a 1 first of all, because this is a way of reading the value of the bit. So we first of all want to read the value, and then we can toggle it, right? So if bit 5 is a 0, we want the output to be a 0. Let me write the 0 here, by using our reference 1. We notice this is quite similar to what we did in terms of when we were doing the digital reading the pen earlier, because we simply want to read the state of the pen, and to read we use the AND gate. because when it is a 1, we expect the output to be a 1. When it is a 0, we expect the output to be a 0. Now, we've managed to read the state of the pin, so we get a current state of the pin, and then we want to put an inverse, which is a NOT gate. So first we do an and then we do a NOT, which is basically an AND. So we read the state, we have a 1. We do an inverse, we get a 0. We read the state, we have a 0. We do an inverse, it will be a 1. So this is how we toggle the LED. So going back to the screen, so back to Tinkercad now. So basically we say, okay, let's comment out the digital write. What we are interested in is to write to a port, and we want port D to be equal to, first of all, are the same. We get our reference, shift it to the LED pin position, which is pin 5 in this case. First, we want to read the state, similar to what we've done before. So we do an AND to read the state of that particular pin. So we have the pin reference, we read the state compared to port D. Now that we've read the state, we want to find an inverse, and to find an inverse or NOT gate, if we go to so bitwise NOT is, so we go back and put it in. Okay, so run the simulation again. Seems to be working fine. Nothing has changed, except that now we've gotten rid of the digital write, digital read. We have suddenly reduced the code to 462. Remember, the loop function and setup function alone took 444 bytes. So the code is pretty reduced now to small space. We are now on 462 bytes. Then we ask ourselves, is there something we can do to improve the code that we have at the moment? So let's see if we can get rid of the setup and the loop. So basically, C, C++, you've got a driver function. You can have several functions. The driver function is your main function. So when the compiler starts, it will work. It will look into the main function, and then it will actually execute what you have in the main function. So let's see, first of all, I want to save this. Now, we want to get rid of the void setup. Get rid of the setup scope. Let's clean this up a bit so you have your comments on there. And then we will get rid of the loop as well. Now, because this inherited the AVR functions, so basically we move our main code into the main function. So because int, the main function returns an integer, which is 0 if the code ran successfully, and another number if there was an error. The return type is an integer, and in this case, we don't need any parameters for the main to use. We don't need them as global variables because the compiler is trying to find them and it can't find them. So we move them into the main function. If we move them into the main function, we run the simulation, then boom, there are no errors. However, if we press the switch, nothing really happening. Is it that nothing is happening, or it's happening so fast that it can't really respond to the circuit that we are actually implementing? What is happening is that our main runs once really quickly and then stop. So basically, it's not in a loop. Remember, when we had the Arduino functions, we were using the loop function, so it could actually loop continuously. So let's take this as our setup on here. So we've got our setup. Now we want to execute the forever loop. A way of doing that is to use a while loop. So we can say a while loop. So while, and we want it to run forever. So basically we say while true or while 1, which means 1 is always true. And then we put that block inside the forever loop. So we initialize here, we jump into a forever loop, and then it will run continuously. So start the simulation, then you press the switch, it works as expected. If you run the code that we have now, we are currently on 152 bytes in terms of usage by the memory usage. So if, let's say, we look at the trends in terms of memory that we've used, when we started off with nothing, it was on 444 bytes. That is how much memory the setup and then the loop alone use. Then our first code, which made use of the digital write, digital read to toggle the LED with a switch, occupied 892 bytes. Then when we started reducing it by using port instead of pin mode, we reduced it to 774. Now, when we added the pull up, we ended up with 680. So just the pull up and a bit more, we went on ahead to add, use the pin to toggle the LED. And first of all, the first LED toggle, writing to the LED if it's low, because it was an if condition, did not change the memory much. But when we toggled, suddenly we reduced the memory to 462. Now with 462, quite similar to the voice setup and loop functions, the memory they were requiring. When we change to int main, we are actually making use of only 152 bytes of memory, which is quite significant in terms of what we have achieved by just using register manipulation.